Imagine an agent dropped into a world it has to navigate, one decision at a time. It sees a situation, it picks a move, the world reacts, and then it has to decide again. Now, before you can teach anything to act well over a long series of choices like that, you need a clean way to describe the problem itself. That description is the Markov Decision Process, and it's the foundation that all of reinforcement learning is built on. Let's unpack it. Here's the thing about an MDP. It's really just a loop between an agent and its environment, repeated over and over. Follow one turn around it, and the whole framework clicks. Everything starts with the state. That's the situation the agent finds itself in right now. The position on the board, the readings from its sensors, the layout of the room, whatever captures where things stand at this particular moment in the problem. Then the agent chooses an action. It follows a policy, which is simply a rule that maps each state to a move. Given where it is, the policy tells it what to do next. Now the environment responds through the transition function. That's the probability of landing in each possible next state, given the state you were in and the action you just took. The world can be uncertain. The same action might not always lead to the same place. So it's phrased as probabilities rather than a fixed outcome. And along with that next state comes a reward, a number saying how good that outcome was. The agent pockets it, observes the new state, and the loop begins again, always trying to pile up as much total reward as it can over time. So why do we even need this framing? Compare it against the kind of prediction most machine learning does. Most models we talk about make a single, one-shot prediction. You hand them one input, they return one output, and they're done. There's no sense of time, no consequences that carry forward, nothing the model does today that changes what it faces tomorrow. Each prediction stands completely on its own. An MDP is built for exactly the opposite. Decisions unfold in a sequence. Each action shifts the state and quietly shapes what comes next, and rewards accumulate along the way. Look, that's the whole point. It captures situations where acting now has consequences later, and that describes most of the genuinely interesting problems in the world, from playing games to steering robots to managing a portfolio. Strip an MDP down to its essentials, and 3 ideas carry the whole thing. The ingredients are 4 in number: states, actions, a transition function, and a reward function. Name those, and you've fully specified the world the agent is learning to act in, with nothing else left dangling. The Markov property is the clever simplification at the core. It says the future depends only on the present state and action, not on the entire history of how you got there. The current state already summarizes everything that matters, which is what keeps the whole thing tractable. Solving it means finding an optimal policy. The agent wants the rule that maximizes expected cumulative reward, usually discounted so that rewards arriving sooner count for a little more than ones far off in the future. All right, let's lock in the essentials. A Markov decision process is the framework that formalizes sequential decision-making, and it's the foundation of reinforcement learning. The framework has 4 ingredients: states, actions, a transition function, and a reward function, all wired together into a single agent environment loop that repeats over and over. The Markov property says the future depends only on the present state and action, so the current state carries everything relevant. Solving the process means finding the policy that maximizes discounted cumulative reward, and nearly every reinforcement learning idea, from value functions to Q-learning to policy gradients, is defined right on top of it. If you enjoy having these foundations made genuinely clear, Standarity.com has plenty more. See you there.